Welcome to The Explainer. Today, we're unpacking a technological concept that absolutely pushes the boundaries of what we even consider possible in hardware and physics. It's called the Ortiz quantum core. Now, if you've heard the whispers about this architecture, you're probably wondering, is this just pure science fiction, or is it a genuine blueprint for the future? Well, our goal today is to strip away all that hype. We're going to look directly at the published research and map out exactly what this insanely ambitious architecture is trying to achieve. We'll explore the staggering performance targets, the grounded scientific building blocks that actually exist today, and what it would literally mean for human progress if this theoretical machine is fully realized. Section 1. The grand concept. Okay, let's dive into this and look at the sheer scale of the ambition behind this chip. 4 times 10 to the 51st power. Just let that sink in for a second. That is a 4 followed by 51 zeros. In the documentation for the Ortiz quantum core, this staggering number represents the imagined target for operations per second. It's a figure so massive it almost defies human comprehension, right? Now, it is absolutely crucial to state right up front that this is a design target. It's an extrapolation of what this architecture theoretically aims to do at its maximum unhindered scale. To really put that into perspective, take a look at this. On one side, we have the concept's goal. On the other, we have today's absolute top-tier classical supercomputers, which operate at around 4.45 times 10 to the 14th operations per second. That gives us a mathematical ratio of roughly 8.99 times 10 to the 36th. I mean, wow. That isn't just an upgrade, that's literally like comparing a cheap pocket calculator to a galactic superbrain. But to truly grasp this, we have to separate the mathematical theory from our current hardware reality. Section 2. Provable versus unproven. Let's transition to grounding these massive claims with a necessary scientific reality check. Because here's the crucial dividing line. That end-to-end performance at maximum scale, that is unproven. There is no published measurement out there proving a single chip of this exact layout can currently hit that 4 times 10 to the 51st operations per second, or, instantly solve any complex math problem. However, and this is a big however, the building blocks are provable right now. Quantum search methods that beat classical brute force, those are real. Modular systems, real. The Ortiz quantum core isn't just some magic wand or science fiction, it's a highly ambitious extrapolation built on very solid foundations. Section 3. The smart maze solver. So let's use a mental model to explain how this architecture practically approaches a problem. Think of the Ortiz quantum core as a highly advanced smart maze solver. Imagine a mathematically impossible search space as a giant, sprawling maze. Classical computers, well, they just wander blindly through every single path until they eventually stumble upon the exit. But this architecture proposes a totally different way. Step 1, it cuts the maze into manageable zones. Step 2, it keeps the walls cool and stable to prevent the whole thing from collapsing. Step 3, it uses light and special materials to illuminate multiple paths all at once. And Step 4, it uses the physics of the chip itself to focus directly on the answer. Instead of wandering blindly, it's designed for making impossible-looking searches actually manageable. Section 4, the scientific pillars. And this brilliantly illustrates the transition into the real, published research that makes this theoretical architecture plausible. The Ortiz quantum core actually sits right at an incredible intersection of 3 major research breakthroughs. First up, modular structure. A 2024 paper from researchers at MIT and MITR demonstrated modular quantum system-on-chip architectures. This is very close to the multi-engine, 48-lobe idea proposed in the Ortiz concept, proving that modularity genuinely helps with scaling. Second, there's the massive hurdle of quantum stability. This was tackled by a 2025 USTC study showing that using graphene on diamond actually improves coherence. The Ortiz core relies heavily on exactly this type of diamond graphene stack. And third, the engine of the whole shebang, quantum search for hard number problems. Which brings us to Diaphantine search. So Diaphantine equations are these incredibly complex polynomial equations where you're only looking for integer or whole number solutions. Classically, finding these can require checking an impossibly large number of possibilities. It's brutal. But recent papers from 2025 and 2026 show that using Grover-style quantum algorithms can provide a provable quadratic speedup over classical enumeration. The Ortiz quantum core utilizes this exact principle, accelerating the search and mapping these incredibly hard integer problems into a quantum space to find the answer vastly faster than classical brute force. So, when we synthesize all of this, the modular MIT research, the USTC diamond graphene stability, and those Diaphantine quantum search algorithms, we arrive at the most scientifically fair and accurate name for this project based on current evidence. The Ortiz quantum core is best described as a conceptual, layered quantum search architecture for Diaphantine and modular quantum processing. Now, I know that's a mouthful, but it's perfect. It keeps the core concept intact and avoids overclaiming those unverified speeds while absolutely preserving the scientifically grounded possibility of the design. Section 5, World-Changing Potential. Let's move to and see how this builds into massive real-world implications if this conceptual machine actually works. In the realm of computing, an architecture like this represents a massive leap in hard problem searching and optimization. It's a total game changer for logistics and scheduling. In materials and sensing, successfully scaling that diamond graphene stack could revolutionize nanoscale analysis and precision navigation. For scientific research, the ability to test massive design spaces simultaneously, rather than one by one, would rapidly accelerate new discoveries. And economically, well, industries that rely heavily on simulation, like pharma companies developing new drugs or logistics firms, would see their optimization times drastically reduced. The ultimate economic impact isn't just about speed. It's about drastically reducing the time it takes to find the perfect solution. So, what's the bottom line? This quote right here really nails the intellectual honesty of where the Ortiz quantum core stands today. It is a bold extrapolation. It's unverified in its full, massive form, but its individual pieces align perfectly with cutting-edge, published research. It's possible in principle, grounded in real research, and currently stands as one of the most fascinating major engineering challenges of our time. Which leaves us with this final thought. Progress often looks exactly like science fiction, right up until the moment it becomes reality. The gap between theory and hardware is definitely wide, but researchers are laying the stones across that gap right now. When bold scientific theory meets the very limits of our engineering, we have to ask what breakthroughs are waiting just beyond what we currently call impossible. Keep questioning, keep learning, and thank you for joining me for this explainer.